This presentation is delivered by the Stanford Center for Professional Development.
Okay, so any question about last time? If not, we'll continue right along. Oh, you should be reading, of course, chapter 4 by now, and in fact, should probably be finished by around today or something like that. So between the homework and the lectures, you should be okay on this. Okay, you can go down to the pad. Last time we looked at linear fractional program. That's a very famous, maybe the most famous quasi-convex problem. There are lots of variations on it, and a variation, this is a generalized linear fractional problem, is you minimize a linear fractional function here. Now here, always in a linear fractional function, you have to decide which sign the denominator has, and by convention, this would be positive. It's positive. But that technically has to be specified. You have to specify the domain. So here's a linear fractional function. You minimize a linear fractional function subject to linear inequalities and linear equality constraints. Now that's a quasi-convex optimization problem, and you can solve it by bisection. That's easy to see, because if you want to know, is f0 of x less than t? That's the question. And so you're really asking, is the optimal value of this problem less than or equal to t? I mean, can it even be achieved, the objective value t? All you do is you take this thing, which is positive, and you multiply it out, and it turns out that's equivalent to the linear inequality like this. Now that's a linear inequality. And therefore, it's a linear, you call it an LP feasibility problem or something like that, to check if the optimal value, if there's an x that satisfies all this and has f0 of x less than t, to solve that, to determine that feasibility problem, you would solve an LP feasibility problem, and then you could bisect on t and solve this. Okay, so that's one way to solve this. It turns out, though, some linear fraction, some quasi-convex problems can actually be transformed to convex ones. It hardly matters, frankly, but in this case, it's good to see how this works. And let me point something out. If you were to take this approach, you'd have to solve an LP for each bisection step. Okay? Now, the number of bisection steps you'd probably have to solve would be somewhere between 10 and 20. 20 would give you 2 to the minus 20 in bisection, and you would reduce your ignorance. That is the difference between a known feasible point and a known bound. You'd reduce that by a factor of 1,000,000. So you'd have to solve about 20 LPs. By the way, for most things, wouldn't make any difference at all. And it's even more than that. Later in the class, you'll understand that when you can actually do something called warm start, which means you'd actually solve one LP, which is very close to the LP you just solved, and it can be done very fast. So the effort is not even a factor of 20. It's probably a factor of 4. So nevertheless, it's interesting, I think, theoretically, and it's actually interesting in practice, that this quasi-convex problem can be turned into actually just an LP. Yeah?
That second line that you wrote, should that C transpose X plus D on our right side, should that be
F? Should it be C transpose? In fact, what on earth should it be? It should be E transpose, like that?
Okay.
Are you happy now? Good. You're happy because what I had was wrong, and this is right. That's good. Okay, thank you. Yeah, it was supposed to be the denominator. It just didn't work out that way. Okay. So let's see how to do this. It's actually very interesting. Actually, this is it turns out this is nothing but the perspective transformation. Or some people call this homogenization. So let's see how that works. What you do is you write down this problem, and let's actually see what happens here. What you do is you write down something, well, here, it's equivalent to this LP. And let me go through the argument, or at least I'll give you some of the argument. The full argument you can find in the book. Here, what you do is you introduce a new, I start with the original problem. Let me just start with the original problem up here. And I'm going to introduce a new variable called z, scalar. I hope this will work. Okay, so I want to minimize C transpose X plus D divided by, this time I'm going to get it right, this. I want to minimize that. Note the period. Everything's cool here. Subject to That's ST, but it means subject to, of course, H, and AX equals B. Now, you know when you do things like you have a quadratic function and you add a new variable that's equal to 1 and to convert it to a quadratic form, I guess that general principle is called homogenization. You make the problem homogeneous by introducing a new variable. So the way we're going to do that is this. I'm going to introduce a new variable called z, and I'm going to say it's 1. Okay? So that's, I haven't hurt anybody. And I can most certainly do this. I guess the z should have gone in front of the h, but you know, it's okay. In loose parsing, you can put a scalar after a vector. Everybody cool on this? I mean, how could you not be? I just multiplied a bunch of things by 1. However, if you stare at this problem long enough, without the z equals 1, you realize the following. It's completely homogeneous. In other words, scaling x and z up here by a positive number has no effect whatsoever on the inequalities, none, has no effect on the objective. Okay? That means, in fact, I can normalize, my current normalization is z equals 1, but I can normalize it any way I want and simply divide out later. It will make no difference. So I'm going to renormalize this problem, and I'm going to renormalize it. Now I am cheating. I'm looking down here. I'm going to normalize it so that this, so I'm going to comment this out, and I'm going to add this constraint in. That's just a different normalization of the same thing. It's just fine. Now, what's that? Z has to be positive. That's correct. Sorry. Thank you. There we go. Actually, technically, z has to be strictly positive. So, in fact, I'll even write it that way, I believe, like that. Okay. Now, if this is 1, the denominator goes away. That goes away. And I am left with an LP here that I have to solve. Is there a question?
Sorry, what's y?
What is y? It's nothing.
Those
No.
Sorry, increments those x.
No. It's just nothing. It's supposed to be x. So it's just one of those days, I think. I have a feeling where yeah, fine, good. Keep me on my toes here. Not apparently that it's going to do any good today, but we'll see what happens. Okay. I should have had that second espresso. I think that was the problem. I didn't. I meant to, but I didn't. Okay. All right. So this is now an LP here. And in fact, if you replace this with this, you get all sorts of information out of this. I won't go into the details, but for example, if you were to solve this and z comes out positive, then by simply renormalizing here, you get the solution. That's the first part. If z turns out to be 0, that's like this one case where this thing is unbounded below or something like that. But that's the idea. So, by the way, this is not a simple trick. But it's actually one that comes up a couple of times. And it's pretty cool that you can do this. Okay. Now, in general, for most, by the way, for most quasi-convex problems, this trick won't work. But for some, it does. Okay. Now we get to the idea of a generalized linear fractional problem. And that's this. You want to minimize the maximum of a bunch of piecewise, of linear fractional functions. And that's on the polyhedron where all the linear, well, it's the intersection of the domains of the linear fractional functions. That's quasi-convex. There's no way to convert that to an LP in general. So that you're going to solve by bisection. And here's an example that's actually quite interesting. So it's the von Neumann growth model. And it works like this. We're going to optimize over x and x plus the following. So x is going to be a set of activity levels. Is going to be a bunch of activity levels. I guess we have to have x positive here too, or something like that. X is a bunch of activity levels at one period, and x plus are the activity levels in an economy at the next period. So that's what these are. Then we have matrices, AX, and AX produces this gives you the amount of AX tells you the amounts actually produced by an activity level x. So this could be, for example, in Rm, if the n activity levels produce, say, m different classes of goods. So if you have an activity level x, Ax is a vector telling you how much goods, the vector of goods produced by that activity level. here. That's AX. Now, when you operate the economy at the next step, that's X plus, are the activity levels. BX plus, that tells you, that's a vector telling you how much is consumed. And then you simply say that the amount consumed at the next stage here, it uses some, it has to use the goods produced in the first in the first stage, so you'd have an inequality that looks like that. Okay. These describe it's a polyhedron, of course, right? The set of activity levels, current and next, that satisfy these inequalities is a polyhedron. And now what we want to do is we want to maximize over these the minimum activity growth level. That's xi plus over xi. So that's what we want to. I guess you know we don't need this because when you write this thing, that's x positive is implicit here. So, okay. So, and to see that this is, I mean, to maximize this is the same as minimizing the negative of this, which is that it's minimizing the max of xi over xi plus. Each of those. So that's the same thing. And that's exactly of this form. That's a quasi-convex optimization problem, and you can solve it directly. So that's one. And what you want to do is you want to set the activities in order to maximize the growth rate of the slowest growing sector. So that's the problem here. And there's lots of variations on this. So, okay. So that ends up sort of problems that are linear and related to linear. Now we move on to quadratic. Oh, by the way, I can tell you what the year is on some of these. The linear programs, as I mentioned earlier, go back to Fourier at least. But the year maybe the generalized linear fractional stuff is maybe the 50s or something like that. Already widely used in the 50s. Quadratic programming is the same. This would be mid-50s. So, okay. So in a quadratic program, you have a convex quadratic objective. That's here. So P is positive semi-definite. And you minimize this over a polyhedron. So a set of linear inequalities and a set of linear equalities. By the way, if you just set P equals 0, you recover an LP. So this is a strict, it's a strict extension of LP. And the picture now is this. Here's your polyhedron, which is your feasible set shaded. And your objective function now, instead of being affine or linear, is in fact quadratic. So convex quadratic. So the sub-level sets are ellipsoids. And so this is showing you the sub-level sets of a quadratic function. Of course, the gradient points downward, down slope, and is the normal to the tangent hyperplane at the level surface. So for this particular problem instance, that's the solution there. And one thing you see immediately that you didn't have for an LP, it's a basic fact, although not of particular importance for us, that in a linear program you can always take a solution that's at a vertex. This is it's kind of obvious geometrically. It's also completely obvious analytically. But it doesn't seem actually to have too much use for us, and in most cases. Although it's made a big deal of, I think mostly for historical reasons. But anyway. But you can see clearly here that the solution does not have to be at a vertex. It can be inside a face. Again, doesn't make any difference to us or whatever. But so this is a quadratic program. We're about mid-50s here is in where we are historically. So let's look at some examples. Well, the most basic one would be just least squares. There's no constraints. That's basic linear algebra. The solution is just given by a solution. I say in the general case is given by this pseudo inverse or Moore-Penrose inverse. That's just A dagger B. But immediately, for example, you can take a least squares problem, and a very common thing, I mean, this is really dumb, but you just add some linear inequalities. In fact, just range bounds. So that's a quadratic program. By the way, what you're going to see later in the class is that, for example, a least squares problem with bounds on the x's, that can be solved basically as fast and as reliably as just a least squares problem. I mean, with a factor, very small modest factor, totally reliable. Okay? Let me actually say something sort of culturally about how the course goes. There's a lot of people that know about least squares. Okay, a lot. I mean, I guess not a huge number, but you know, there's a lot of fields where least squares is widely. A lot of people know about least squares in signal processing, statistics, communications, machine learning. It goes on and on and on. A lot of people know about that. Okay, you just throw in something as dumb as this, ranges on the x's, and that number of people who recognize that as basically a problem that is completely solved, is just technology. I mean, we can just solve that period. Drops by at least a factor of 10. Okay? What you will find instead, do people have things like this? Sure they do. Of course, what they do is they do heuristics. They either invent their own algorithm that's impossibly long, might actually work, but it's fantastically complicated. Or they make some iterative thing with regularization. And I mean, you wouldn't believe what happens when people encounter things like this. Okay? And people make a big deal out of it. There's no reason for it. So I think the 0th order thing to do is to look at a problem like that and say QP. Therefore, we're done. It's just done. There's almost nothing interesting to say about it. You'll write code that solves this. It'll be 30 lines. It'll be totally reliable. So there's not a big deal. But it has, at the same time, it has huge practical uses, right? So if you want to do parameter estimation, but you have bounds on the x's, here's a stupid one. Suppose you're estimating powers or intensities. Well, these are, generally speaking, non-negative. So that's just like non-negative least squares. And that's just, so for us, that's just a QP. But I'm telling you now, that's already, you've moved into a much smaller group than the people who know about least squares. For example, a whole huge thing in statistics, this is just amazing actually to me, but whatever. So that's the constraint that the x's be ordered. Okay? So, of course, that's a set of n-1 linear inequalities. I think you had it on some homework, like homework 1 or something. I don't know. Right? That's just a set of linear inequalities. So, believe it or not, there's a whole subfield called isotonic regression or something. There's books written on this. Literally, on minimizing, on doing least squares with that. Right? Why is there a book on it? Because it's you know, because there's no analytical solution like there is for just ordinary least squares. It comes up enough or whatever anyway. So I don't, you know, for us, monotonic regression, that's below the level I would even assign as a homework problem. No, I would go that low. But it would be one of it. When we're counting up like the amount you have to do in a week, that would count for like nothing, very little. So anyway, and whole books on it. So, okay. So I'm just mentioning these things are simple, but actually so far this has not diffused out to a lot of application areas. Just people haven't gotten the word yet, which is very strange to me, that you can do this and it is completely straightforward. So, okay, we're back on track here. Here's an interesting one: is a linear program with random cost. So that's another. Let's do a specific example. If you want to make a specific example, let's do diet. The infamous diet problem. So x represents the amounts of a bunch of foodstuffs you're going to buy, something like that. And there are constraints. There are things that have to balance out exactly, and there's inequalities. Of course, this can include lower bounds and upper bounds on, for example, nutrient levels and things like that. So our constraints become a polyhedron in x here. Now, what we're going to the problem now is that when we're going to formulate this diet now, but we're going to implement it, I don't know, next month, and we don't know the prices of the foodstuff. So it's not as simple as saying just minimize C transpose X, which would give you the cheapest diet that would meet the requirements. Okay, because you don't know C. You should know something about C. C, for example, has a mean C bar, but it also has a covariance sigma, something like that. And it doesn't. I mean, this doesn't matter here. There are many things you could do. In practice, I'll tell you what would probably be done would be that. You would simply ignore the variation and just work with the expected values. Now, it's not hard to imagine that that could be a seriously bad choice because it's very easy to do. All you do is you take one foodstuff or one component or whatever, and you make it slightly cheaper than another one that has similar nutrients. But you make it have much more price volatility than the other one. Everybody see what I'm saying? The LP will, if you ignore the risk, this is price risk. If you ignore the price risk, The LP, of course, will use the cheap stuff based on this expected value. But anyway, so that's an extreme example, but I mean, that's the kind of thing you could do. So what you really want to do is trade off mean price and price risk. And this would be done, we'll do more of this later, by simply minimizing a weighted sum of the expected cost and the variance here. Gamma is a risk aversion parameter, and there's lots of ways to figure out what it is. And for that matter, you would probably solve this problem for a whole family of gammas and get a trade-off of expected price versus the variance in the price. And then you select based on your risk aversion where you should operate on that curve. So that's the point. Okay. So, but if you work this, if you take a look at it, it's nothing but this is a QP. There's one condition. Gamma has to be positive here. Otherwise, this becomes this is no longer convex. Okay. So what's interesting about that is that you can do risk-averse design by convex QP. But you can't do risk-seeking. If this were negative, it would be risk-seek. If gamma were negative, you'd be doing risk-seeking. You'd actually prefer, if there's two diets that have about the same mean cost, meet all the constraints, you'd actually prefer, in risk-seeking, you'd actually prefer the one that has higher variance in cost. So fortunately, that's not something you want to do. So it turns out, once again, what you want to do lines up with what you can do. I should make one other comment here, and that's this, that in general, but by the way, not entirely always, if P is not positive semi-definite, so if it's got just literally one negative eigenvalue or something like that, or something like that, this problem goes from being extremely straightforward to NP hard. So if you know what I'm talking about, that's fine. If you don't, I will just say this. It goes from a problem that is in theories, actually multiple theories, would assert that problem is now very hard to solve, and also in practice. You'd go from a problem where you can solve the exact solution if x can be huge, like 10,000 by 10. I mean, that's just no problem. The 30-line code you'll write to solve this, for example, will easily handle that. If this becomes indefinite, you can solve these problems. But for example, with x in R20, you'd have to have a lot of luck and a big old cluster, and you might get the answer, later that day. So you're just in a completely different regime. If x is 100 is in R100, when p is indefinite, this problem essentially becomes impossible. So convexity makes all the difference with quadratic programs. Okay. Now another generalization. I mean, it's kind of silly, but is a QCQP. That's a quadratically constrained quadratic program. So here the constraints can also be quadratic, convex quadratics. Now here, if these are 0, you recover a QP, and of course if all the p's are 0, you recover an LP, a general LP. Here, these things, if p is positive definite, of course this represents an ellipsoid. So here the feasible set is an intersection of, well, ellipsoids and degenerate ellipsoids. Now a degenerate ellipsoid is one that can have a flat face and be infinite. So a half space is actually a degenerate ellipsoid, for example. But for example, if P is positive semi-definite but only has rank 3, this is sort of a degenerate ellipsoid. It means that in n minus 3 dimensions, it's sort of infinite. In three dimensions, it's got curvature. So for example, it would be a cylinder in R2, for example. R3, sorry, a cylinder in R3 would be a degenerate ellipsoid. That would be generated by a rank 2, a 3 by 3 matrix P, that's rank 2. And this inequality would then be not a cylinder, but it would be an ellipsoid like this, and then it would have an infinite extent in another direction. Okay? So that's it. It's a convex problem and can do this. Okay. Now we get to the first thing. Again, this is we're still in the mid-50s. Okay, now we're jumping ahead. Now we get to well, depends how you want to count the history. But you're into the 90s now, so this is new, roughly. Although, actually, there's papers written in the 50s that refer to this. They knew how to do it when there was one inequality like this, but not in general. So let's take a look at this. A second-order cone program. This is SOCP. There was a confusing while, by the way, in the 90s, when these were referred to as, some people were trying to call these QPs, and it never stuck. But there's a brief period with a brief group, a small group of people where they tried to get this to be called QP. I mean, which is fine, but it just didn't fail. And it seems like SOCP has won out as the term. So here it is. You minimize a linear function subject to, and the constraints are quite interesting. It's the norm of an affine thing is less than or equal to an affine thing. Notice, very important here, it is not norm squared. If this was norm squared, this problem would be a QCQP. Okay, this is not norm squared. That's the square, this is sort of the square root of a convex quadratic. That's what this thing is. Okay? And it's called second order cone programming because each constraint is nothing but this. You have an affine mapping that maps x into AIX plus BI, that's a vector, comma, and then a scalar, CI transpose x plus DI, and that should be in the unit second order cone, the Lorentz cone in Rn plus 1. Okay, so that's each of these constraints. Now, this is more general than everything we've seen so far. It includes, well, not the linear fractional. It includes linear programming. That's obvious because you just make that 0 here. It includes linear programming. You can rewrite quadratic programming, and you can write QCQP in this form. But it's more. There are problems you can write as an SOCP. You cannot write as any of these. So this is a real extension. There's also something very interesting to point out here. If you write the if you rewrite this in sort of our standard form, that's AIX plus BI minus, I guess you'd write it this way, right? Minus CI transpose X minus DI is less than 0. So this would be Fi of X, okay? That would be our standard form to write this. Here's a very interesting fact about Fi of X. It's not differentiable. This is the first problem you've seen that has that feature. Looks differentiable. I mean, well, it actually, this function, of course, that's affine. That's differentiable everywhere. By the way, when is the norm differentiable, the 2 norm? Where is it differentiable? Where is it not differentiable?
Not differentiable at the origin.
It's not differentiable at the origin. Okay, is it? How about everywhere else? No, it's happily different. It's analytic everywhere else. It's got derivatives of all orders, right? And in fact, just think of the graph. The graph is like this ice cream cone. It's perfectly smooth, no problem, except for that tip. Okay? So, by the way, you might say, oh, come on. That 1 point makes that much difference? This is like, what are we? Are we in the math department? Only a mathematician would worry about that one. I mean, these are the kind of things you would think but not say. You'd say, come on, what kind of a person, what kind of a human being would worry about this 1 point where it's non-differentiable out of all of Rn? Okay. So what do you think of that? Just not worry about it. Well, obviously that argument is totally wrong. It turns out what is interesting about second order cone programs is that, of course, the solution is very often at the point. Obviously, if you have pointed things and you optimize things like linear functions, of course you end up at the point. So, yes, these functions are non-differentiable at only 1 point. Well, okay, whenever AI transpose X plus BI is 0, it's non-differentiable. However, it turns out that's where the solutions lie. That's what makes this useful in applications and so on. So it's not just something, well, people in math are correctly interested in the non-differentiability. So this is a non-differentiable problem. By the way, it would be completely unknown how to solve this efficiently, let's say in 1988 or something like that. There were some people who knew about it by 1988 in Moscow. That was about it. So now it's completely routine. So it's as if it's always been here. So people do this all the time. By the way, I think it's in Excel now. So give you a rough idea of what's happened. Well, a lot of these things actually are. Okay. Okay, let's look at an example of second order cone programming. So very interesting, it's this. Let's start with a linear program. That's minimize C transpose X subject to AI transpose X less than BI. And what we're going to do is we're going to add the idea that there's uncertainty in C, AI, and BI. And in fact, you know what? We'll just think we'll worry about uncertainty in the A and B. By the way, earlier in the diet problem, we're worrying about cost variation. I'll just make C fixed, and I want to worry about variations in the AI. Okay? By the way, if you want to go back to the diet problem and figure out what that would mean, what would it mean that there'd be variations in AI? I mean, in terms of a diet problem. What's the implication? What would it mean? What does it mean?
It'd be like maybe there's variation in how much nutrition you like absorb from a certain food.
Exactly. Okay, that's exactly right. So the point is that when you get some food stuff and you analyze it on Monday and Tuesday and Wednesday, it's it's close, but it's not the same. And therefore, if you compose a diet, actually, and you ask for so many calories or whatever, and you form it this way, if you just use the mean, you might not actually, on a sample-by-sample basis, actually have the number of calories you want. In fact, the number of calories is a distribution. So that's exactly what it is. So it might be nutrient variation or something in the foodstuffs. Okay. Actually, pretty much any LP that's ever solved, here's the way it works. The coefficients in AI, the actual numbers in it, by the way, so often they are 0. And by the way, when they're 0, they probably really are 0. It basically means, if the third entry of A1 is 0, it means that X3, the third variable, doesn't enter into the first constraint. And the 1s, by the way, often also have the flavor of being actually 1, because you're sort of adding something. And typically the -1s too. Actually, when you see a -1, it typically really means -1. Any other number you see is probably traces back, if you trace the provenance of that number, it will go back to something which is not known. It'll go back to some analyst or some estimate of a price. It'll trace back to some geometry and some Young's modulus or whatever. Trace back to all sorts of crazy things. But if for sure, any number like that has some variation. You might know it within 1%. You might even know it within 0.1%. It depends on the field and application. But it's not at all uncommon that you would not know it to like 10%, for example. So that's just a point that it's quite realistic to have this to model variation in data in a problem. Okay. Now you can do this lots of ways, and later in the class we're going to look at this in much more detail, but this is just for now just an example of SOCP. Two common ways are this, and it's strange. People argue about which is better, and of course the answer depends on the application. So in a deterministic model, here's what you do, is you would say something like this. You would say that each of the AIs lies in an ellipsoid. That would be something like an uncertainty ellipsoid. And you would insist that the constraint hold for any AI in the ellipsoid. Okay? And so the other names for that would be like a worst case model or something like that. That would be. Now, by the way, the people who would do this would go and give you long philosophical arguments. They'd say the greatest advantage of their approach is that they don't assume a probability distribution because there aren't any, blah, blah, blah. They go on and on with this. Or it's a worst case. It doesn't matter. Detractors would say, oh, that's way too conservative because you're assuming the worst thing, that when you buy all these foodstuffs and put them together and blah, blah, blah. Anyway, it's all makes no sense. Then the other model, of course, is stochastic. So here, you'd say AI is a random variable. And this is called a chance constraint. You'd require that the constraint be satisfied with some high reliability. So eta might be 0.9, more common to be 0.95, 0.99. You might even see 0.999. And by the way, the embarrassing thing is that these two are not that far apart because, for example, if that's 0.999 and you have a 3 sigma ellipsoid and you put that over here, you're very close to doing the same things, but it doesn't keep these people from, they still fight with each other. So that's the, and it's very strange because it doesn't make any sense at all. It depends on the application. What's the cost of violating the constraint and so on and so forth. So it all depends. All right. So now, it turns out both of these turn out to be SOCPs, second order cone programs. And the way you do that is this. Let's parameterize the ellipsoids as a center plus the image of the unit ball under a matrix PI. So this is one parameterization of an ellipsoid. And then the robust LP looks like this. It says minimize C transpose X subject to AI transpose X is less than bi. That's for all a in this ellipsoid. Oh, by the way, some people make a huge big deal out of this. What they call this constraint here, they call that a semi-infinite constraint. Got it? So now, why is it semi-infinite? Because you see, this represents a single linear inequality for each element of an ellipsoid. And there's an infinite number of points in an ellipsoid. Did you know that? So that's why this is a semi-infinite thing. And anyway, so, I mean, big deal, right? Although, it doesn't keep people from writing whole books on it. And, okay, that's just, anyway, I'll go on. But this is easy when is it true that AI transpose X is less than BI? Let's fix X, you fix B. A varies over this ellipsoid. When would this hold for every element in the ellipsoid? You have to check whether AI bar plus PIU transpose X, whether that's less than BI for all U of norm less than 1. Okay? But that's easy to do because this is nothing but AI bar transpose X plus, and then I'll make it this way. I'll write it as U transpose times PI transpose X, like that. Now, if I want to maximize this over all U with norm less than 1, that's a constant. This is an inner product of U with a vector. And so, obviously, by the Cauchy-Schwarz inequality, this thing, the largest that number could be, is the norm of PI transpose X. And by the way, the worst U would be PI transpose X divided by norm PI transpose X. That's the worst U. Okay? So I plug in the worst value and I get this, and I insist that that should be less than BI, and that is right here. Now, if you stare at this closely, you'll realize that's an SOCP. Because you have just what you have a norm, two norm of an affine function, and a linear and a constant. It's SOCP. And by the way, let me tell you a little bit about what the implications of this are. People can solve SOCPs now basically as fast as LPs. So almost as fast. I mean, certainly for all reasonable, for huge numbers of situations, it's the same speed, same reliability, everything. That means people can solve robust LPs now, basically at no additional cost, little additional cost over an LP. That has lots of implications. By the way, it is that fact, or that observation, is propagating out. So it has now hit finance. So that's why SOCP solvers are in Excel now. So, because whenever you solve basically, if you're solving an LP, then you ask the person, how well do you know the data? If they don't say perfectly, and if they do, they're probably a liar. But if they don't say perfectly, then you say, oh, then you should be solving an SOCP. And actually, a lot more people these days will say that's exactly what we're doing. So, okay. So this actually has important, lots of practical consequences. It's not fully diffused, but it's getting there. Okay, let's look at the stochastic approach. So in the stochastic approach, we'll assume that the constraint vector is Gaussian with mean AI bar and covariance sigma I. Now, when you form AI transpose X, that's just a scalar Gaussian random variable. Depends on X, of course, but we're fixing X. It's got mean AI bar transpose X and variance sigma X transpose sigma I sigma. And so the probability that you meet your constraint is equal to the CDF. That's a normalized random variable, of course, right? That's BI minus AI transpose bar. This is the probability. That's a normalized random variable, something like that. This one, and then you put BI here. And this gives you the probability that you meet this constraint. Okay? So these so-called, oh, by the way, these are called chance constraints. That's one name for this. And problems that generally involve constraints that involve probabilities of something, that's a whole field called stochastic programming. This one actually is complex enough to actually, in my opinion, deserve a field name. That's not true of some of the others. But this is actually complicated stuff, and I'm okay that there's whole books written on this. All right. So, but in this case, in this simple case, we can write this out analytically as this, and it's an SOCP. Actually, it's interesting. It's an SOCP provided the inverse CDF of a Gaussian evaluated at eta is positive. That happens for eta bigger than 50%. So actually, it's extremely interesting. We can do chance-constrained linear programming. In other words, I can have a linear program with Gaussian random constraint vectors. And I can impose the constraint that, that each constraint is satisfied with a certain probability. The important part is if that probability has to be more than 50%. By the way, which corresponds exactly to risk aversion versus risk seeking. Right? So the one we're really interested in, probably, is eta equals 0.95, 0.99. These are the ones we're really interested in. We're probably not interested in 10%. That's risk seeking. Anyway, it doesn't matter because we can't solve the problem with 10% risk aversion anyway. Okay. So our next topic is geometric programming. By the way, for all of these, there's no reason, you should have read the chapter. So this should not be the first time you're seeing these things. You should not be following everything I'm saying because I'm going fast. But I assure you, all of these problems you will encounter multiple times during the rest of the quarter. So, you should just be kind of getting a rough idea here. You'll see all of these again. But don't be concerned if I'm going fast, is what I'm saying. Okay. Geometric programming. This is an interesting special class of, we'll see, they transform to convex problems. This also, by the way, has a long history, goes back into the 70s. Actually, this goes to the 60s, including the first book written on it is super cool. It's this book where it's a whole book on geometric programming. I'll say what it is in a minute. But the whole book, in the last paragraph of the book, it actually says, literally like in the last paragraph, it says, it's entirely possible that someday these problems could be solved using a computer. It says that. The whole book is about these cases where you would solve it by hand, by various ways. But it's very cool. And by the way, they had it exactly right. So this has a long history. Actually, probably elements of it were known in statistics probably in the 60s. Right, but okay. And it comes up in a lot of other fields. It's kind of it's a weird thing. When you first see it, you'll think, I have never, ever heard of such a thing. But once you start looking for these, they're like everywhere. Or they're in certain fields, they're everywhere. But, all right, here's what it is. So unfortunately, there's some deeply unfortunate nomenclature here. But it came from the 60s, and nothing we can do about it now. So just for the record, right, a monomial, people in math have been using the word monomial for 400 years or something like that. And it always means the same thing. It's, a product of a bunch of, it's a single term polynomial. Okay, so it has always meant the same thing. There's absolutely no idea as to what, monomial would mean. But they decided they would take this term, which everyone agrees on has a meaning, and extend it. So in the context of geometric programming, or GP, you have to be very careful, though, with GP, though. If you type GP into Google, you're going to get several things. You're going to get geometric programming, but you're also going to get something called genetic programming. Very different. I better not say anything about it. We'll just move on here. So in the context of GP, as in geometric programming, you have something called a monomial function. It's a local definition, so don't ever say this outside, in public or something like that. Don't ever say that like x to the 1/2 is a monomial, because if there's anyone, unless you're only around people known to be talking at that moment about geometric programming, because you'll sound like an idiot. It'd be like changing the word polynomial or something like that, and say, well, that's what you call a polynomial, but I call a polynomial this. Anyway, so here's what's a monomial. It's a positive coefficient times a product of variables, each one to a power, and the power can be anything. It can be an integer, it can be irrational, and it can be negative. Okay, so that's a monomial. This does come up in a bunch. Obviously, it's clear this comes up in a lot of engineering. These are like people call this a scaling law or something like this. Depends on the field you're in, right? It's a scaling law or something. Okay. Okay. Now, again, don't look at me. This was not my idea, just for the record. They came up with this thing called a polynomial, which, first of all, sounds stupid, number one. And it also is stupid because it's supposed to combine positive and polynomial. Okay? I mean, that's okay, fine, you know. But the point is, these aren't even polynomials because the exponents here can be like minus 0.1, and they can be 1.1. So anyway, I guess languages are living, and that's a stupid name, and it stuck. So polynomial, there it is. It's a sum of these things. So, you know, an example would be something like this, okay? Here, there. That's a monomial. Okay, that's a monomial, and here's a polynomial, right? x1, x2 plus, you know, square root x2. Here, there you go. And there's a polynomial in this thing. Okay. Here is a GP, a geometric program. You minimize a polynomial subject to some polynomial inequalities less than 1, and a bunch of monomials are equal to 1. Okay? Now, you might ask, why the 1? As 0 had been our standard before. There's a real good reason. The theory of GP with right-hand side 0 is a very short theory because monomials and polynomials are always positive. So the branch of GP where the right-hand side was a 0 here didn't go very far because all such problems are infeasible. Okay. So that's a GP. Now, by the way, this is not remotely a convex problem. For example, you could say minimize square root x and finish with some stuff down here. That would be a GP. Okay? Obviously, it's not convex. Square root x is concave. Okay? So these are not convex problems. However, these can be changed by a change of variables. These can be converted to convex. Okay? And this is it. And it's actually quite interesting, the conversion, and it's not at all unexpected. So, you know, if the variables are positive, you should have at least a slight urge to take the log. I mean, that would be normal. So if the variables are positive, we'll just take these variables yi, so that xi is e to the yi. And then let's see what happens. We're also going to do the same thing. We're going to minimize. Well, you can put log in front of anything you minimize because log is monotone. And I could put log fi less than or equal to 0. So now our friend 0 is back on the right-hand side. Okay? So, but let's see what happens. What is log of f0? And I'm going to write this in kind of a, I'm overloading some notation. That's the vector whose entries are e to the yi. Okay, so the question is, what is this thing? Well, let's take a monomial, and let's take the log of this monomial. Well, you get log c, that's b. Then you get plus, and then you get the exponents. You get a1 log x1, but log x1 is y1. So when you change variables by this logarithmic transform, and you take the log of a monomial, you get an affine function. That's good. Now take a polynomial. So here I take the log of a sum of these things, but that's the same as log sum x of an affine function. Okay? Because each of the x's I replace with e to the yi, like this. Then I take a sum of those things, and I take the log. That's log sum x. That's this thing. And if you look at this function is convex in y, because it's log sum x of an affine function of y. So it is definitely convex. That's not remotely obvious, by the way, here. Not even remotely obvious. I mean, it is once you've seen it and all that. But in fact, articles on geometric programming that didn't understand that it converts to convex programming by a change of variables persisted until like the early 80s. Okay? So this is not so obvious. Okay, so what that means is this GP over here, which is not remotely a convex problem. I mean, also look at the equality constraints. The equality constraints would be things like, you know, x1 to the 0.3, x2 to the minus 0.7, x3 to the 1.2 is equal to 1. Well, that has no place in a convex problem. Only constraints you can have only equality constraints you can have in a convex problem are affine, or linear. Okay, so, but it transforms to a convex problem, like that. So it just transforms right to a convex problem. And it's actually, it turns out, by the way, GP comes up in lots of fields. It comes up in statistics and machine learning all the time. It has to do with exponential families and maximum likelihood estimation. We'll also see that it's intimately connected to entropy type problems. We'll get to that. It comes up in information theory, but it also comes up in circuit design. It seems to be completely ubiquitous. And it comes up in power control and wireless. So I'm just mentioning this, right? And we'll see a lot of these later.
How did you get from the monomial f transform into the log is equal to a transform?
Here? How did I?
One step down in between.
Can you go down to the pad here, and I'll go over that real quickly down here. If you, so the question was, how did I get? If you go down the pad here, I'll just work this out. Okay, I'll just describe it. So you take the log of a monomial, and the first term, oh, you can see it. I see, but maybe it's not on. Okay, so that's fine. If you can see it, that's fine. But for those of you who are sleeping right now, this is what happens when you sleep through the class. There we go. Okay, great. There we go. All right. So what we're going to do is we're simply going to take the log of this. That's log c plus a1 log x1 plus ... plus an log xn. But log x1 is y1. So I get exactly that. So that's how that transforms. Okay, and let's see. What I was saying was that it comes up in a lot of applications. Once you're sensitized to GP, you'll start seeing it all over the place. In fact, kind of in any problem where the variables are positive, they represent powers, intensities, or something like that, densities. You can start thinking how GP might come into play, and we'll definitely see lots of examples of these, of GPs. Actually, they're quite. It's quite interesting because they're quite natural. For example, in wireless, and we'll see examples of this, but for example, in wireless power allocation or something like that, the x's are going to be the powers of transmission. For that, or they could be like they could be the powers allocated to channels in some big in some big multi-channel system or something like that, or different frequency bands. And what this transformation says, I mean, if someone's doing optimization, they say, you know what, it's better to work with the log of the powers. But that's what engineers have been doing for like decades and decades, because these are called decibels. So it says you should work with decibels. No one would be surprised by that. And then the constraints would be things like that signal to interference ratios should exceed like some factor. When you take the log of the constraint, you're basically saying that you should write your constraint this way, that the signal to interference ratio should exceed 8 decibels. Again, that's how they would do it. People don't say that SIR has to be bigger than like 2.8. They say it's got to be bigger than 8 dB or something like that. So it's actually interesting that exactly the way people who would actually work in these fields would use these things turns out to correspond precisely to the convexifying transformation of variables. So we'll see lots of examples of this. Okay. Let's look at a mechanical example. And it's design of a cantilever beam. So here you have a bunch of segments. This one just has 4, but obviously you'd have lots more. And what we're going to do is this. It's going to be so it's going to stick straight out, and a force will be applied to the tip. And 2 things will happen. Of course, this thing will deflect. And we're not going to do the huge, horrible deflection. We're going to do the small deflection so that we can use linearized approximations. So it'll deflect substantially, but we'll assume we'll use linear models and things like that. It will deflect, and there'll actually be a strain, stress, well, both, on each segment. Okay? And what we want to do here is, obviously, if I design, the thicker I make the cross sections, obviously the stiffer the beam. Yeah, stiffer meaning if I apply a force here, it deflects less, and the stress is less. Okay, so if I make it a big, thick thing all the way out. And you can easily, you probably have a pretty good idea intuitively of what you want here. You certainly wouldn't want a beam that looks like this, that tapers out like that, because now you're putting a whole bunch of weight over here. Actually, you're just making it much worse. You probably want one that tapers like that. And I think just, this is just completely intuitive. So the question is going to be to get the optimal tapering of a beam. That's it, cross section. We're going to design the shape of a beam, cantilever beam. Okay, so we'll minimize the total weight, subject to, and what we'll do is we will, and we're going to actually, these have a width and a height, so that there's a height, And I know very little about mechanics, except I do know I do know that sort of the strength of well, from carpentry, I know that the strength of this thing goes up like the cube of the height, for example. Beyond that, I'm sure there's people here who know a lot more about this than I do. So, okay, so we'll have upper and lower bounds on the width and the height of the segments. We'll limit the aspect ratio so you don't get like an infinitely thin thing like this. We'll upper bound the stress. And we'll upper bound the vertical deflection at the end of the beam, which is actually where the maximum deflection occurs. So that's the same as the deflection. Now this is actually quite a complicated problem. It's highly nonlinear and so on and so forth. But let's see, it's actually a GP. And to see how that works, we look at the total weight. Now these are variables. By the way, what kind of function of W and H is that? Again, outside the context of GP, if someone walked up to you on the street, what kind of function of W and H is that? It is a function of W and H, and I want to know what kind it is. Linear? No. No. It's linear in W if H is fixed, and it's linear in H. So this is not. Well, maybe it wasn't clear. There wasn't two questions, so I'll say it again correctly. What kind of function is this of left paren W comma H right paren? And what's the answer? It's quadratic. Okay. Is it convex quadratic? Hey, wait a minute here. You should not hesitate. What? No, it's not. It couldn't possibly be. What kind of quadratic form does this have? There's nothing on the diagonal. Diagonals would be things like Wi squared, Hi squared. There's nothing on the diagonal. It's blocked. It's like 0, diag, 0. Now, do you really have to think whether a matrix like that is positive, semi-definite? I don't think so. Positive semi-definite things need non-negative on the diagonals. Of course, this has 0 on the diagonals, but there's a rule. If you have a positive semi-definite matrix and it's 0 on the diagonal, that row and column is 0. So this has split eigenvalues. So, okay, so this is a quadratic function of W and H. But it is not remotely convex. It's got split eigenvalues, or concave. Okay. However, it's a polynomial, because each of these is a monomial, and it's a sum with positively weighted blah, blah, blah. It's a polynomial. So that part is cool. Now, the aspect ratio and inverse aspect ratio are monomials. So if I set them less than a number, I could divide by it, and I'd get a monomial. Well, they're polynomials, so I can make an inequality of them. That's fine. And the maximum stress is given by this, and that's a monomial here. Now the vertical deflection and slope are it's quite complicated to actually work out how much this thing, the tip, deflects as a function of the width and height of each of these beam segments. Very complicated, okay? But it's given by a recursion, and the recursion looks like this. It says you take VI, and it's 12 times I minus a half here. I think this. Let's see. That's okay. In this case, this is for I equals 1 to 4 here. No, this is for I equals 1 to n. Sorry. This is everything's cool here. Take VI is this thing. It's F over. That's a constant. E is Young's modulus. Wi. These are the variables. So this term. Hopefully I can get this right. Yes. Okay. What is that term? In GP terminology. What's that? What is it? Monomial. That's a monomial, right? It's got a positive coefficient in front because I is 1 is the smallest thing here, right? F is positive. It's a positive force on the tip. Young's modulus positive, and then it's actually W to the minus 1, H to the minus 3, Hi to the minus 3. Okay, so that's a monomial. And now you add this one. It's going to go from the tip back, plus this. So actually, recursively, here, the first one is a monomial. The last one is a monomial. Then going backwards, you take a monomial and you add it to the previous one. So by recursion, the VIs are monomials. Polynomials. They're all polynomials. They're sums of polynomials all the way to the front. Then you can get the YIs this way. Well, each yi is the next one. Well, in the first one, it's going to be this plus that. In fact, in the last case, it's actually a monomial. So the last yi is a monomial. And then the second one is polynomial, and all the others are polynomial. So what that says is that this is these are very complicated expressions. You wouldn't want to see them written out, but they are indeed polynomials, all of them. So that's actually quite interesting. It's not remotely obvious, and let me say some of the things that it implies. That's not obvious, and I really doubt, I think I can say with extremely high probability, there's absolutely no one in mechanical engineering, including someone with super good, long design history and stuff like that, would know this. And let me just say one of the things you can conclude right away. It says that if you have two designs, two cantilever beam designs, so imagine two. One is quite wide and high, and it makes no difference what they are. I'm going to form a compromise design from the two beams. However, what I know to do is the following. I know I should take a log of everything. So the compromise design, instead of taking like Wi and Wi bar and taking the average of the two, actually my compromise design is going to be the geometric mean. Because I know I really should be working, the problem mathematically is more natural in the log of the variables. So if you have one log width, you have another, I should take the average of the log widths and then take the exp of that. That's the geometric mean. So it says the way you should blend, so the first thing it says is the way you should blend two cantilever beam designs is by geometric mean. Okay. By the way, that fact alone is like not obvious at all. And then it has then there's a stunning conclusion about it. It would be this. If we're solving this problem, if you have two designs that meet all these specifications, these are fantastically complicated. I mean, when you start talking about like the tip deflection and stuff like that. Two designs that do it. If you take those two designs and form a blended design given by the geometric means of the other ones, I can say something about the total weight of that blended design. I can say that it's less than or equal to the geometric means of the weights of the two designs. Okay? So for example, if those were two different designs that satisfied the constraints and had the same weight, that blend could only be better than either of them. Everybody see what I'm saying here? So, by the way, in other areas, I've always tried this. I go to a field, I find someone who alleges to be a good designer with lots of experience and stuff, and I talk them through what the implication of geometric programming is in their field. And in only one case, it was Mark Horowitz, who actually said, yeah, that makes sense. He didn't say it right away either, by the way. And I believe him. This is in the context of circuit design. I really believe him. He says, no, that makes sense. That's how you blend that's how you blend two circuit designs, and so on. So maybe there might be someone actually who does enough mechanical engineering that this would at least not sound stupid. Actually, it never sounds stupid, right? The question is whether or not, because you can make very strong statements about what happens when you make these blended designs. Okay. Now, that's just one of the implications of what it means to be a GP. Okay. So how do you write this as a GP? Well, that's a polynomial directly, and you write out all the inequalities, which I won't write out. I won't go through this anyway. You can go through this yourself. Let me look at one. I'm going to look at one more example of a GP. It's a more generic one, also very interesting example. I don't know any practical uses of it, but there might be some. Actually, I've been itching to find one for years. Never have. Here it is. Let's take a matrix that's element-wise positive. So a square matrix element-wise positive. So you might know about something called Perrin-Frobenius theory if you've had a class on Markov chains or something like that. But I'll tell you what it is. Basically, it's this. It says that the eigenvalue of A is not symmetric, so it can have complex eigenvalues. But it says that the complex value of largest magnitude, that's its spectral radius, is that magnitude, it's positive, number one. And also the associated left and right eigenvectors can be chosen to be positive. So that's Perrin-Frobenius theory. How many people have seen this in some context? I'm just sort of curious. No, okay. That's all. Anyone? Markov chains. Somebody took a class on Markov chains, right? What did they say about that? Really? Come on. They didn't do. They didn't. I mean, they didn't mention this. Oh, okay. How do you know that the steady state equilibrium distribution is positive, or non? Well, in this case, positive. This is a strong form. Where did you hear about it?
A Markov chain class.
Markov chain class. Here? No. It's not looking good for Stanford, is it? Yeah. Where was that?
University of Washington.
University of Washington. Okay. All right. So this is and this is called the Perrin-Frobenius eigenvalue. It's positive. And of course, what it does is it tells you the asymptotic growth rate of a to the k. So if you take powers of the matrix, if it's a dynamical system with positive entries, it says it'll tell you the growth rate. So for example, I mean, this would come up in lots of dynamical cases. This would be, for example, an economy. It would tell you how an economy, or it might tell you how a multi-species system would work. Actually, the condition that A should be element-wise non-negative means that everything is, I guess you would call it excitatory, and nothing is inhibitory. I don't know if those are words, but you know what I mean, right? So it means you start with a positive X. These are left concentrations of something, and the concentration of anything does not inhibit the growth of anything else. So it would just lead to it or something. It would increase it. It would be excitatory. So in that case, a to the k tells you how this dynamical system would propagate, and the asymptotic growth rate, which could be negative, by the way, it is simply completely determined by this number. If this number is 1.05, it says that by the time you do this 100 steps, you've grown like 1.05 to the 100. If it's 0.96, it asymptotically decays as 0.96 to the k. So that's what this is. Fantastically complicated function of A, right? Because you calculate the eigenvalues of A, which is to mean you form the characteristic polynomial, which as a function of the entries of A, you don't want to see written out because it has, something like n factorial terms. That's number one. You then have to you have to find the roots of that polynomial, which again, you can't do if n is 5 or bigger, because there is no formula for the roots of a polynomial of degree 5 or bigger. Okay, so, and then once you get these n roots, you want to take the absolute value and take the maximum of them. And I think by now you should be convinced this is a fantastically complicated function of the matrix A. Okay. Well, another way to characterize this is that the Perrin-Frobenius eigenvalue of a matrix is it's the smallest lambda for which a v is less than or equal to lambda. By the way, for some positive v, if you, by the way, it turns out here, the first thing you actually end up showing is it's that, and that turns out you never get inequality here. It's always equality here, which of course makes sense because now lambda is an eigenvalue, like that. But what's amazing is you can now minimize the Perrin-Frobenius of the Perrin-Frobenius eigenvalue of A, where the entries of A are themselves polynomials by making a problem that looks like this. You minimize lambda subject to A of x sum aij, and these are all monomials in the variables, which are x, v, and lambda, and these are polynomial inequalities. Okay, so basically log sum x comes out of this. That's how that works. So, and you can make up some fake applications of this, I suppose. I think we attempted one in the book or something like that. But you can. It'd be nice to actually find a real one somewhere. That's a challenge, by the way. Okay, so I think what we'll do is we'll quit here. But let me say just a few things about where we are. We're sort of marching through all these problems. You will get to solve in a theoretical and in a numerical and practical sense every type of problem we're talking about multiple times. So we'll be doing all this for the next 7 weeks, actually. We'll be doing this stuff. So this is just your first introduction.